Hashtag Quantum Computing Progress long-form tutorial script. You're probably thinking quantum computers are still decades away. But here's what you need to know: major breakthroughs are happening right now, and they're about to change everything. Stay with me because I'm breaking down exactly where quantum computing stands today, what's actually possible right now, and why you should care about this technology. Let's start with the reality check. Traditional computers process information using bits, zeros, and ones. Simple, predictable, fast for everyday tasks. But quantum computers? They operate on something called qubits. These qubits can exist as 0, 1, or both simultaneously. This property, called superposition, is what makes quantum computing potentially revolutionary. According to Google Quantum AI's December 2023 announcement, their Willow chip achieved a major breakthrough in quantum error correction, demonstrating exponential improvements in reducing errors as more qubits were added. This matters because error correction has been the massive roadblock preventing quantum computers from scaling. Here's the problem most people don't understand: quantum computers are incredibly fragile. Qubits lose their quantum properties through something called decoherence. Think of it like trying to balance a pencil on its point: one vibration, one disturbance, and it falls. For years, the more qubits you added, the more errors you'd get. It was a death spiral. You couldn't scale the technology because scaling made things worse, not better. That's why Google's achievement is significant. Their Willow chip showed that they finally broke through this barrier. They added more qubits and the error rates actually went down. Per IBM's official 2024 quantum roadmap announced in January, IBM is actively scaling toward quantum processors with over 1,000 qubits and developing modular systems for practical, real-world applications. This isn't theoretical anymore. Let's walk through what's actually happening in the quantum computing landscape right now. First, understand the current players. Google, IBM, and other companies are racing toward what's called quantum advantage, the moment when a quantum computer solves a problem faster than any classical supercomputer. Google claims they've achieved this with specific applications. IBM is taking a more measured approach, focusing on building reliable, scalable systems. Second, the applications are becoming clearer. Quantum computers could revolutionize drug discovery by simulating molecular behavior. They could optimize massive logistical networks, imagine completely rethinking how supply chains work. They could crack current encryption systems, which is why cybersecurity experts are already preparing for the post-quantum era. Third, the timeline matters. We're not at quantum computers in every home yet. We're at specialized quantum computers in research labs and corporate facilities solving specific, high-value problems. This is the near-term phase, and we're living in it right now. If you're finding this valuable, hit that subscribe button. We post tech tutorials daily, and I've got more deep dives on emerging technology coming soon. Now, here's where it gets practical. What can quantum computers actually do today? They can model quantum systems, molecules, materials, chemical reactions. A classical computer trying to simulate a quantum system has to account for exponentially growing possibilities. A quantum computer simply runs the simulation natively. This means pharmaceutical companies can test thousands of drug candidates in simulated environments before physical trials. They can optimize complex problems. Imagine a logistics company with millions of possible delivery routes. Finding the genuinely optimal solution is computationally impossible for classical systems. Quantum computers can explore multiple solution paths simultaneously. They can search unsorted databases exponentially faster than classical computers through something called Grover's algorithm. This might sound abstract, but it has massive implications for everything from financial modeling to cybersecurity analysis. Here's what's crucial to understand about the current limitations. Today's quantum computers are what experts call NISQ devices, noisy intermediate-scale quantum devices. They're powerful but imperfect. Error rates are still high. The quantum states are fragile. You can't just throw any problem at a quantum computer and expect it to solve it instantly. You need specifically designed quantum algorithms that leverage quantum properties. The hardware is advancing rapidly. Superconducting qubits dominate the current landscape. These are tiny circuits cooled to near absolute zero where quantum effects thrive. Other approaches like trapped ions, topological qubits, and photonic systems are under active development. Each has trade-offs between coherence time, error rates, and scalability. The software ecosystem is growing. IBM's Qiskit, Google's Cirq, and other quantum programming frameworks are becoming more accessible. You don't need a physics PhD to write quantum code anymore. The abstraction layers are improving. The real timeline looks like this. For the next few years, quantum computers will solve increasingly complex optimization and simulation problems. They won't replace your laptop. They'll complement massive data centers. Companies will rent quantum computing time from cloud platforms, similar to how cloud computing works today. IBM is already offering quantum computing access through their cloud platform, with real researchers running real experiments. By 2030, we might see quantum computers handling practical problems in drug discovery, materials science, and financial modeling. The systems will be larger, more reliable, and more integrated into enterprise workflows. Here's a pro tip that most people miss. If your company handles complex optimization problems, molecular simulation, or advanced data analysis, start exploring quantum computing now. Not because you'll deploy it tomorrow, but because the learning curve is steep. Understanding quantum principles, learning quantum algorithms, building your team's expertise, this takes time. The organizations that start experimenting now will be positioned to leverage the technology when it's truly mature. Another advanced point: quantum computing won't replace classical computing. It'll complement it. Hybrid systems that use both quantum and classical processors together will likely dominate. You'll have a problem. Identify the portion that benefits from quantum processing, send that portion to the quantum computer, get the result, and feed it back into your classical system. This hybrid approach is already being implemented in research settings. One more thing: quantum computing has massive implications for cybersecurity. Current encryption relies on mathematical problems that are hard for classical computers but potentially easy for quantum computers. This is pushing the development of post-quantum cryptography. NIST has already released standards for quantum-resistant algorithms. Organizations handling sensitive data should start transitioning to quantum-safe encryption now, before large-scale quantum computers exist. The bottom line: quantum computing is transitioning from theoretical physics to practical technology. The breakthroughs are real. The limitations are also real. We're in the early industrial phase, comparable to where classical computing was in the 1950s. Revolutionary potential, but still specialized, expensive, and requiring expert knowledge. The opportunities are in understanding this technology now, positioning your organization to leverage it, and preparing for the security implications. This is how you navigate your tech journey with confidence. You don't wait for technology to mature completely. You understand it, experiment with it, and prepare for it. Remember, at TechNavigator Pro, we believe in helping you navigate your tech journey with confidence. The future of computing isn't waiting. Make sure you're not either. Subscribe for more breakdowns on emerging technology, and I'll see you in the next video.